Hi guys, in this video we are going to continue on the Unit 5 atomic structure. So last video we did talk about a lot of common elements. We try to know their name, their symbol, their appearances, and their hazard nature. Alright, so today we will continue on talking about more the atom and how, what is it made of, something like that. But before I actually start, let's talk about the difference between element and atom, right? So what is the difference between element and atom? Actually, we did talk about the definition of the two type of substance. Now, let me again clarify once more. So, for example, when we have carbon, okay, carbon. Now, carbon, if we are able to zoom in, so until we see all the particles inside, we will see carbon actually consists of a lot of these carbon atoms, and they are arranged in a very closely packed in a very orderly manner. All right. Now, for carbon, because if we find out that there are only consisting of one type of atom, which is the carbon atom, only one type of atom. Therefore, carbon is an element. Okay, carbon is an element. Because you remember, the definition of element is that it is a pure substance consists of one type of atom only. And we cannot split it into anything simpler by chemical means. So even though you can cut it into half, it is still carbon atoms. It is still made up of carbon atoms. So in terms of the composition, it doesn't get more complicated, doesn't get more simpler, right? So this is what we call cannot break it down into anything simpler, okay? Now, so every single carbon atom here, every single unit that made up of carbon is what we call the carbon atom. Okay, so atom, we will define it as the smallest unit of matter, and everything is made up of atom. Okay, so that's the difference between element and atom. Or rather than saying that difference, actually this is like the meaning of element and atom. Okay, now here we try to learn more about the structure of atom. Now, just now I said that atom is the smallest unit of matter, right? But, you know, even atom is composed of other things. So there are some building block that forms an atom. Now, we say that an atom is made up of something called subatomic particles. Subatomic particles. Okay, so a couple of these subatomic particles, when they join together, they will form an atom. Okay, so there is actually something smaller than atom. Okay, so just now I said that atom is the smallest unit of matter. In secondary school level, it's still okay, but actually you will know that for an atom, it is composed of something even smaller, which is called subatomic particles. Okay. Now, we say that an atom is composed of three subatomic particles. They are called proton, neutron, and electrons. Okay, let's give you the Chinese name of it because that is a little bit meaningful for me. Okay, so this one is called this one. Okay, this one, and then okay. So these are the Chinese name. All right, so all the atoms are made up of these three subatomic particles, except for one, for hydrogen. So some hydrogen atom does not have any neutrons, does not have any neutron. Okay, so it only contains, this is U, it only contains proton and electron. Okay, now down here, if you look at this diagram, so we can describe the structure of an atom by having a nucleus and having the electron on the outside. Okay, so in the middle of an atom, it is the nucleus, and on the outside, on the surrounding, we have electrons moving around. Okay, Now, if we further break it down, this structure, we will see something like this. In fact, you see the nucleus is made of proton and neutron. So the proton and neutron, they are located at the center of an atom. On the other hand, the electrons are moving around on the surrounding of an atom. Okay? So electrons on the outside, proton, neutron on the inside. Okay? Now, if you look at this table, we try to show some features of these subatomic particles. So proton, neutron, electrons, first of all, they're symbols. Sometimes we want to use simpler representation of these three subatomic particles. For proton, it is P positive, neutron just N, and then electron is E negative. Okay? Now the positive, negative obviously has its own meaning. So let's have a look. Now first of all, we look into the mass, like how heavy it is. Now here, 1, negligible. Negligible means more or less equal to 0. So light that you can actually forget about it. We call it negligible. Okay? Now first of all, what do you mean by 1? What do you mean by 1? Is it 1 gram, 1 kilogram, 1 pound? Now the idea goes like this. We say that atom is very small. So when it comes to the mass, you can expect to see the mass would be very, very light. We are talking about like 1 times 10 to the power negative 26 or 23. Okay, so light, 23. So if we are talking about the actual mass in grams, in kilograms, then it will be quite inconvenient for us to compare, right? So the scientists, the chemists, come across with an idea. They try to use something called relative mass. So what they did is they will set up the mass of proton being 1, just 1, okay? And then they try to compare the mass of other subatomic particles to that of proton. And it turns out that neutron has exactly the same mass as a proton. Therefore, if proton is relative mass having 1, then neutron is also being 1. So that is the idea. That is the concept of relative mass. And when we try to compare electron, the mass of electron with proton, it turns out that electrons is around 2,000 times lighter than the proton. So light that we can say that, okay, we can forget about it. So let's just say it is like 0. Okay? So that's the idea about relative mass. Now, because it is a relative concept, because we try to assume that proton having a mass of 1, then it actually bears no unit. Okay? It is just imaginary. We just make it up. It's fake. Okay? It's all comparative sense. So that's why no unit. So whenever the question asks you about relative mass or relative blah, 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 there is no unit. So bear in mind of that. Okay? Now, on the other hand, relative charge. Now, I think you get the gist of it, the concept of relative. So again, proton, neutron, electron, they're so small. So when we talk about the actual charge, it's going to be very, very small. So instead of using the actual mass in terms of coulomb, coulomb is the unit of charge, we actually use relative charge. So we assume that proton is positive 1, and we try to compare the charges of other subatomic particles. And it turns out that neutron is having exactly no mass, no charge. On the other hand, electron is having exactly equal charge of proton, but it bears an opposite charge, which is negative. So this is how the relative charge are being set up, okay? And again, because it is in relative sense, it bears no unit, okay? And lastly, the location. We say that both proton and neutrons are located in the nucleus at the center of an atom, but the electron is moving around on the surrounding of an atom. So that's the idea, okay? All right, so now I understand there is a lot of new terms and new numbers, right? You may not necessarily know why. I will put it this way. A lot of these are like the rules, like how things work. Excuse me, how things work. So it would be best if you try to accept it and play by the rules, then everything would be easy to handle. Okay, at this moment, try not to ask so many questions like as to why it is +1, why is it like -1, but is actually a very difficult question. It's definitely beyond the scope of DSC, so don't bother. Okay, so just play along. All right. So here, atomic number, mass number, full atomic symbol. So here we try to introduce different ways to represent an atom. Actually, not different ways, but just one very useful way to represent the atom. So right now here, we try to figure out a way how to represent an atom using a very simple representation, and with just one symbol, it is able to entail like 6 informations in total. So let's see how it works. Again, play by the rules and everything would be fine. So first of all, here, if you look at this one, this is a full atomic symbol. This is what we call full atomic symbol. Okay, this one, He42. Okay, now what does it mean by that? So first of all, the bottom left corner is what we call atomic number. Atomic number. Okay, so what is atomic number? Atomic number, if you have a periodic table, which is at the back of the notes, you see all these are the elements, and all of these elements will have a number on the top left-hand corner. And this number is what we call the atomic number. Okay, so atomic number basically show its position on the periodic table, just like that. But you may ask, hey, how do we assign these atomic number? Do we just assign them based on the year of discovery, or do we assign them based on alphabetical order? Actually, this atomic number is based on the number of proton. The number of proton. So here, atomic number is actually equal to the number of proton. Okay, the number of protons. So if the atom consists of, let's say, 4 protons, then the atomic number is 4. Just like that. Okay? Now, for mass number, the mass number is the sum of protons and neutrons. Let's put it down first. Okay, sum of protons and neutrons. So first of all, mass number basically means the mass of that particular atom. Okay, the mass of that particular atom. So the mass of an atom, you can tell, must be the total mass of all the subatomic particles, right? Because atoms are made by subatomic particles. So if we know the total mass of all the subatomic particles, then that would be the mass of the atom, right? So in other words, it is the total mass of proton, neutron, electrons, okay? But just now, if we go back to here, we say that the relative mass of electron is negligible. That means we can take it as 0. So that's why the total mass of an atom, we only concern about the total mass of proton and total mass of neutron. Okay? Now, also, because we have defined it, the relative mass of a proton being 1 and the relative mass of neutron also being 1. That means if we have like 10 protons, then the relative mass will be 10. If we have like 20 neutrons, then the relative mass will be 20. So that means the mass of protons equal to the number of protons. You get it? Or the mass of all the neutrons would be equal to the total number of neutrons. Okay? So that's why down here, the mass number is the sum of the number of protons and neutrons. For example, if you have an atom having 10 protons and 11 neutrons, again, 10 protons, 11 neutrons, then the mass number will be just 10 plus 11, which is equal to 21. Okay? That's the idea. Now, what about this He then? Now you see that 4 is the mass number, proton plus neutron, 2 here is the atomic number. What about the He here? Now the He here is the chemical symbol, okay? or the atomic symbol, okay? So the atomic symbol is exactly the symbol that you can find it from the periodic table, okay? Or actually some of them you should have already memorized it since the last video where we introduced a lot of common elements and I also put down the chemical symbol, isn't it? So these are all the chemical symbols. It's the simplest way to represent the identity of the element, okay? So here He, if you go back to the periodic table, it is helium. Now, you say, sir, hey, I don't have the English name. Actually, later you have to memorize the first 20 elements. Okay, this is required in Form 3 chemistry. Do we have this periodic table in our exam? Sorry, we don't have it. We do not provide a periodic table for you. So later on, you need to memorize at least the first 20 elements. Okay? Now, so going back to here. Now, like I said before, this full atomic symbol can use to represent six informations. So let's find out which six information. Okay? So supposingly, you have this one, 4,2 helium. So the first thing you're going to know is, I'm going to jot down some notes here. So related to this, okay, we will know first of all, okay, the chemical name or the corresponding element. So like which element does this atom belongs to? This one is helium. Okay, helium. So the second thing we know that is the atomic number. So the atomic number is 2. You just look at the bottom left corner. And from there, we will know the number of proton, which is equal to 2 as well. Because you know, atomic number equals to number of proton. Okay? Now, number 4, we also know one more information, which is number of electrons. Number of electrons, how do we know? Here, the idea is, if you look at the bottom line here, we say that an atom must be electrically neutral. That means no net charge. What do you mean by no net charge? Again, if you go back to here, we say that proton is having a positive 1 charge, electron is having negative 1 charge, right? So an atom must be electrically neutral. That means if you have like 10 positive, you must as well have 10 negative. So altogether there is no net charge. That means if you know the number of protons, you also know the number of electrons because these two has to be the same. Okay, so that's why going down here, if you know that there are 2 protons, then you will also able to tell there are 2 electrons. Okay, so we can also put down here, an atom must be electrically neutral, therefore that number of proton, which is positively charged, is equal to the number of electrons, which is negatively charged. Okay? Now, so after that, after knowing all these 4 information, the 5th information is, of course, the mass number. So the mass number equals to just this top left-hand corner, which is 4. Okay? And last but not least, the number of neutron. Now, number of neutron we cannot directly get from the full atomic symbol, but you can tell mass number is proton plus neutron, and atomic number is just proton. So if we have mass number subtracted by the atomic number, then we can cancel out the proton and the rest of them will be the neutron. Now, this is more of a mathematical explanation. In a more chemical perspective, in a more chemistry perspective, you know, the mass number essentially is the total mass of this atom. And the mass of this atom is determined by the number of proton and neutron. So if you know the sum of it, and you know how many protons you have, then you may as well know the number of neutrons. Okay? So the number of neutron equals to 4 minus 2 equals to 2. Okay, so this is how we can get all 6 information from the full atomic symbol here. Okay, so right now I have a little practice for you. So for this one, this is chlorine. Okay, so can you also figure out all these 6 information for this particular atom? Okay, you can pause the video and try it yourself. You can write the answer in the empty space here as a practice. Okay, so let's have a look at the answers. So here, first of all, this is Cl, and Cl is chlorine. Okay, and then we need to know the atomic number. The atomic number is, you look at the bottom left corner, so this one is 17. Okay, if you know the atomic number, you will also know the number of proton, which is also 17. Okay, because number of proton equals to the atomic number. And also, if you know the number of proton, you also know the number of electrons, which is also 17. Okay, because it has to be electrically neutral. And lastly, not lastly, the second last, you need to look for the mass number. So the mass number is the bottom left, is the top left-hand corner. This one is 35. So lastly, the number of neutron is equal to 35 minus 17 equals to 18. Okay, so this is how it works. Okay, now after that, let's look at next page. Okay, so let's look at next page. So here we have a practice question. Again, my advice is you try to pause the video and try it yourself, and then we will check the answers. Okay. All right, so let's check. So first of all, boron, we have the atomic symbol, we have proton, neutrons, so we have to work out the full atomic symbol. So the full atomic symbol for boron, first of all, the chemical symbol is B, and then from the number of proton, we know the atomic number, which is 5 over here, and lastly, the mass number, which is the sum of proton and neutron, so we have 11 here. Okay, easy. Now for sodium, similar idea. So the symbol is Na. Okay, so atomic number equals to number of protons. So it is 11 on the bottom left corner. And then we have the mass number, which is equal to the number of proton plus number of neutron, which is 23. Okay. Now for argon, so it is Ar, and then atomic number is 18. And then the mass number is 18 plus 22, which is 40. Okay, very easy. Now bromine, similar idea. We have Br, and the atomic number 35. The mass number is 79. Okay. Now here, this time, they give you the full atomic symbol and ask you to fill in all these blanks. Now, first of all, atomic symbol basically is this one, the P. Okay. And then the number of proton is equal to the atomic number, which is 15. And you have the mass number, 31, you have the atomic number, 15, then the number of neutron is basically 31 minus 15, which is equal to 16. Okay? And lastly, nitrogen, we have N, and the number of proton is 7, number of neutron, basically 14 minus 7, which is, again, 7. Okay? So this one should not be too difficult. Okay. Now the next thing we're going to do is we need to talk about the electronic arrangement. So the idea goes like this. Just now we say that the electrons, okay, they are in the surrounding, right? They're moving in the surrounding. The question is, so surrounding is quite vague, right? It's quite ambiguous. So, nucleus is at the center, right? So, what about electrons in the surrounding? Would it be here? Would it be here? Would it be here? Would it be here? Would it be like somewhere over there? Okay. All these places are surrounding, right? So, but you won't expect the electron to be going far away from the nucleus. it has to be maintained in a certain distance, right? And it turns out that electrons, they actually are moving in a certain predicted position. Okay, so there is an area, or to be more precise, an orbit, where the electron is actually traveling. All right, so they are not in random position, they actually at a certain position. Okay, and it turns out that electrons, they are located into something called electron shell. Okay, so if you go to these two diagrams or these three diagrams, you see we have a lot of this circle, right? A lot of this circle, and the electrons, they are all located on this circle. You won't see any electrons lying in between those circles. So what are those circles? Now those circles is what we call electron shell, okay? Or we can simply say shell, okay? Now a shell doesn't really look like a shell of a snail or of a tortoise. It's more like an orbit, the route of the electron that it would take as it moving or revolving the nucleus. Like this is the path it takes, all right? So to us, we can think about it as the position, the location where we have a high chance of finding this electron because they're moving around, okay? So this is basically the place where they are, okay? Now, knowing that we have specific shells, so our next question is, how does this electron arranged on this shell? Are they all packed together in one of the shells, or are they like evenly distributed across the shell, or should they all occupying like the middle shell? Okay, actually there are a set of rules we have to follow. Now the first rule is the electron must be put in the innermost shell, first. Okay, so in this case, the electron is put onto the first shell first, and then to the second shell, and then to the third shell, and then to the fourth shell, so on and so forth. So the first shell is defined as the shell closest to the nucleus. The second shell is defined as the second closest shell to the nucleus, so on and so forth. You may ask, hey, why do we have to put it in the first shell first? The reason is because the first shell, the electron is closest to the nucleus, and the nucleus is having a positive charge due to the proton, so the electrons in the inner shell is attracted much more stronger than the positive nucleus, and therefore that particular electron is more stable. So like this is the reason why electrons must be put in the innermost shell first, and then we put into the outer shells, okay? Now, however, there is a problem being the innermost shell. Even though it is the most stable one, the problem is it is the smallest. It is the smallest shell. That makes a lot of sense. It's simple mathematics, right? It's the circumference, right? So the inner the shell is, the smaller it is. So the question is, how small? In other words, how many electrons can we put into the smallest first shell? There is an equation. You guys know equations, right? So 2n squared. Now, I don't know why when I printed out the square kind of fall down a little bit. So it should be 2n squared. So if you have a first shell, then you can substitute n equals to 1. Then you calculate it. So 2 times 1 squared, that gives you 2. So that means the first shell, it can hold maximally 2 electrons. Okay? And then it will become full. The second shell, on the other hand, you can substitute 2 into the n. We get 2 times 2 squared equals to 8. That means the second shell, we can put at most 8 electrons. Okay? The third shell will be 18 electrons. The fourth shell will be 32 electrons, so on and so forth. Okay? So when the electrons are to be assigned to the electron shell, it has to follow, first of all, the inner shell first, and then moving on to the outer shells. And secondly, we have to pay attention to the maximum availability of each shell, like the maximum number of electrons each shell can hold. Okay? So That's the idea. So if you look at some examples here, okay, for example, helium, it has altogether 2 electrons. Why is it having 2 electrons? It's easy, because when you check the periodic table, helium, the atomic number is 2, right? So that means it has 2 protons. When it has 2 protons, it has also 2 electrons, right? So we have 2 electrons to arrange onto the shell. So with 2 electrons, we can simply put it all into the first shell, and then it's done, right? So that's why the electronic arrangement, basically the arrangement of electrons would be 2, okay? Now, for boron, on the other hand, it has 5 electrons again because it is having the atomic number 5. So that's why it has 5 electrons. So how do we arrange them on the shell? So first of all, we can put 2 electrons into the first shell, so the first shell is full. And then we will put the remaining 3 electrons onto the second shell. Then everything will be settled, okay? The electrons will be happy, okay? That's the idea. For sodium, it has 11 electrons to be allocated. So again, 2 electrons put into the first shell, 8 electrons put on the second shell. And we have 1 more remaining. So we may put it onto the third shell, okay? So that's the idea, that's the rule, okay? Now, all this electronic arrangement, okay, we call it electronic arrangement, is very important. It's very important. Later on, when we do like Form 4 chemistry, Form 5 chemistry, like DSE chemistry, now I can say it right now. I can be like a forecast, okay, like a prophet. So, in fact, I tell you what, chemistry is all about electrons. It is all about electrons. The arrangement of electrons determine its physical properties. The movement of electrons determine its chemical properties. Okay. Now, at this moment, of course you don't understand what I'm talking about, but maybe at some point, if you study DSE chemistry, at some point, as you learn more chemical reactions and properties, maybe at a point you will remember what I said today. Like, actually, everything is about electrons in chemistry. Okay. Hopefully, at one day you can appreciate that. You can understand what I'm trying to say. If you understand that, congratulations, you get pretty good chemistry ability then. Okay. Going back to here. So, why are we so concerned about electronic arrangement? Because we say that the electronic arrangement determines the chemical properties. Okay? Actually, the physical and the chemical properties. But here, I try to emphasize on the chemical property. Okay? That means how an element reacts depends on the electronic arrangement. So, chemistry is all about reactions, right? So, of course, electronic arrangement is important because it determines the chemical reactions. Okay, so that's the idea. Now down here, this is the way we represent the electronic arrangement. So you see, like 2, 8, 1. Okay, 2, 3. What does it mean by that? So actually, for example, the 2, 8, 1 here. So it means here, first shell. Here, second shell. Here, the third shell, so on and so forth. Now, do we have to put down like comma 0 for the fourth shells? We don't have to because there are no electrons there. So we're only concerned about the occupied electron shell, So here, that means we have 2 electrons onto the first shell, 8 electrons onto the second shell, and 1 electron on the third shell. So that's the idea. Okay. Now down here, this guy, if you are smart, you may realize, hey, sir, is it wrong? Is it wrong? Because, hey, sir, 20 electrons, so 2 electrons onto the first shell is full, okay? 8 electrons onto the second shell, then it is full again. Perfectly fine. But what about the third shell? Like third shell, according to what we discussed before, it can hold 18 electrons at most. So why don't we have 2, 8, 10? 2, 8, 10. Sounds pretty good, right? Now, we would say that it is a special case. It's a special case. There are two special cases in DSE, which you need to memorize, which are the potassium and the calcium. Okay, so let's put it down here. Special case. So, first of all, it is the potassium. So it's K number 19, and also the calcium, Ca number 20. So these two are special case. So you may think, oh, it is 289, right? Because it's 19 number, so 289. But sorry, this is wrong. The correct answer is 2881. Okay? Similarly, for calcium, so 20 electrons, you may expect to see 2810, right? Sorry, again, it is wrong. The correct version would be 2882. Okay? That's the idea. Don't ask me why. Of course, I know why, but it's, again, beyond the syllabus. Just to give you one more, what about scandium? Scandium is Sc21. So some of you may think, okay, 2811, of course, it is not correct. Some may think, I know this time, 2883. Haha, must be like this. Sorry, wrong again. It turns out that it is 2892. This is correct. Mind blown, right? Mind blown. You don't have to know why. You don't have to know why. It's just like this. It just happens to be like this. If you really want to know why, you can ask me later. It's talking about something called orbitals, subshells, something like that. Okay? So that's the idea. So hopefully, you are able to assign the electronic arrangement for the first 20 elements. Okay, first 20 elements. Now, for today's video, I will stop it here. And next time, I will talk more about this one, okay, the electron diagram, and also we want to practice more on the electronic arrangement, okay? So I will stop it here today. Bye-bye.